Alright, so today we're going to be learning about de Moivre's theorem. So de Moivre's theorem is a theory in complex numbers that allows us to take powers of complex numbers in a much faster way than what we would do in Cartesian form. So we know when we have complex numbers in Cartesian form, that to say square them or cube them or raise them to a power, we have to use our binomial expansion laws, and it can take quite a long time. De Moivre's theorem allows us to take powers of complex numbers in a much faster way, and it does this by, first of all, applying the power to the complex number in modulus argument form. So de Moivre's theorem states that if z is r cos theta plus I sine theta, then z to the power of n is equal to r to the power of n cos n plus I sine n. So what that's telling us is that if we have a complex number, we can apply de Moivre's theorem by raising the modulus of the complex number to the power of n and multiplying the argument of the complex number by n. So if we want to find the Cartesian form using de Moivre's theorem, we first of all have to convert it to modulus argument form. We can see in this question it's already done. So applying de Moivre's theorem, it's going to be 2 to the power of 5 cos of 3 pi on 10 times 5 plus I sine 3 pi on 10 times by 5. So 2 to the power of 5 is 32. And then we've got cos. Now 3 pi on 10, 3 on 10 times 5 is 3 pi on 2. So cos of 3 pi on 2 plus I sine 3 pi on 2. Now there's a couple ways of converting it now into Cartesian form, but the thing we're going to realise in this example is that 3 pi on 2 is exactly 270 degrees in degrees if we went from radians to degrees. But if we think about our Argand diagram or our Cartesian plane, 3 pi on 2 is going straight downwards. That's implying that if we go straight downwards, we do not have an x or a real component, it's just an imaginary component. But since 3 pi on 2 is going straight down, it's going to be minus 32. Now again, I like to abstain away from using your calculator that will work for these questions, but it is always good to check. If you do type that complex number into your calculator, it will give you minus 32. So question number 2, yes, again, you could use your calculator, but we need to develop the skills of how to do these questions without your calculator, because if you're relying on your calculator to do this question, especially the new one that can do square roots in exact form, then you're not really grasping how a complete understanding of this concept. So to do this, I would first of all convert it to modulus argument form, and I would do that by drawing a cute little diagram. So over here, we're going to have root 3. The real component is 3, and the imaginary component is 1. We put our theta there, and we're going to say tan of theta is equal to 1 on root 3. Taking tan inverse of that, hopefully we should all know tan inverse of 1 on root 3 is 30 degrees, or pi on 6. So this complex number we should also find if we called it the complex number z. The modulus would be the square root of 3 squared plus 1, which is 2. So this is the complex number 2, and I might write it in shorthand, 2 cis pi on 6. So 2 cos pi on 6 plus I sine pi on 6. We're raising that to the power of 6. We get 2 to the power of 6, which I believe is 64. Yep. And then we've got cis pi on 6 times 6 is pi. So we've got the complex number 64 cos pi plus I sine pi. Now, again, let's think about our exact value trig. Now, of course, you could just think about your what a cos of pi is. You could also type it into your calculator. But if you think literally in terms of your diagram, the argument of pi is going around by 180 degrees. In other words, we're starting at the origin and going straight to the left. That's implying that there is no y or imaginary component, and since we're going to the left, it's minus 64. Again, I'm just going to quickly type that into my calculator and see if we do get minus 64. So yes, it will give you the right answer, but please make sure you understand how to do it like I am, and I would expect that you show this in an exam. This question here. So we're asked to find the product of these two complex numbers, but individually raised to different powers. Now, yes, you could do this by hand. You could apply, say, the binomial theorem to the first thing, and then your perfect square for the second thing. But let's have a crack at using de Moivre's theorem. We're going to do that by first of all converting it to modulus argument form. So we draw our little diagram. I think we already figured this out. So, not quite. That was the other way around. So we've got the real component of 1, the imaginary component of root 3. So tan of theta is root 3 on 1, which I'm pretty sure is pi on 3. Yep, so theta is 60 degrees or pi on 3. And if we call this complex number z, it would have a modulus, again, of 2. So this first complex number is 2 cis pi on 3, and we're still raising that to the power of 4. The second complex number, now you might already be able to tell that this is going to be root 2 cis of minus pi on 4, or 7 pi on 4. But let's have a think. So we've got 1 and 1. So tan inverse, or I've got tan of theta, first of all, is 1, which means theta is pi on 4. However, we've got to consider our quadrants. And since we're in the 7th quadrant, not the 7th, pardon me, since we're in the 4th quadrant, that would make our principal argument, the argument with the principal axis, to be either minus pi on 4 or 7 pi on 4. Both are acceptable. And we can see if we called this the complex number z, again, it would have a modulus of the square root of 2, 1 squared plus 1 squared. So this is root 2 cis, I'm just going to say 7 pi on 4 squared. Now we can apply de Moivre's theorem. So we raise 2 to the power of 4 and get 16. Cis of pi on 3 times 4 is 4 pi on 3. Multiplied, root 2 squared is 2. Cis of 14 pi on 4. Okay, the next step, and you can see why it's so much easier to convert this into mod arg form, is because this step we simply can apply our multiplication rule of complex numbers in modulus argument form. So we multiply our moduli and we get 32, 16 times 2. Cis, we add the argument, so 4 pi on 3 plus 14 pi on 3 is 29 pi on 6. Again, to get that on my calculator, I just typed in 4 on 3 plus 14 on 3. No need to type in the pi, because then your calculator is going to give you a decimal. So that's a nice and easy way of adding those two fractions without doing it by hand. Then I might think about, okay, 29 on 6 as a fraction is 4.833333 repeater. Now we know that the range in radians, obviously the maximum range for one revolution is 2 pi. And 2 as a fraction or as a decimal is 2.0, we know that. But 29 on 6 is 4.83. So this argument is greater than 2 pi. So we know, hopefully, that we can keep subtracting 2 pi until we get a number that is within our range. Now, if you subtract 2 pi twice, you get 5 pi on 6. If you subtract it 1, you only get 17 pi on 6, which is still not less than 2. So 5 pi on 6. Now, an advantage of initially having your argument as minus pi on 4 is if you add those two arguments together after you've applied de Moivre's theorem, often you will get this 5 pi on 6 initially instead of having to minus 2 pi a couple of times. So that is an advantage of using your negative angles, or your angles between pi and minus pi. So let's draw a little diagram to consider where 5 pi on 6 is. Now the fraction 5 on 6, hopefully we'd all know, is about 0.8, which is in the second quadrant. So that argument of this complex number is 5 pi on 6, which would make this pi on 6. If we have a go, we've got a modulus here of 32. So we're going to say this complex number is 32 cos 5 pi on 6 plus I sine 5 pi on 6. Now, we're going to apply basic right-angled trig here to find the x and y components. So we're going to go, okay, the x component is 32 cos of pi on 6. Now, cos of pi on 6, let's quickly check, is root 3 on 2. So this in the x direction is root 3 on 2. And in the y direction, I'm pretty sure sine of pi on 6 is a half. Good. So we're going to say this is the complex number, 32 multiplied by root 3 on 2 plus I of a half. However, if we look at this in terms of its position on the Argand diagram, you're going in the negative x, or the negative real direction. So we're going to make this a minus. Multiply that 32 through, and we get minus 16 root 3 plus 16i. Okay. The next one, again, we're going to convert our complex numbers into modulus argument form. Then we're going to apply de Moivre's theorem. And then it looks like we're going to have to apply our division rule in modulus argument form. So that's when we divide the moduli and subtract the powers. So if we draw two cute little diagrams here, minus 1 plus I, you might already have memorized that this is going to be root 2 cis of 3 pi on 4. So theta goes there. 1 goes here and 1 goes there. Tan of theta is going to be 1, so theta is pi on 4. However, this is in the second quadrant, so our argument, if we call it the complex number z, is going to be pi minus pi on 4, or 180 minus 45, which is 3 pi on 4. The modulus, remember the modulus of any complex number with 1 and 1 is going to be root 2. So the modulus, if this was the complex number z, is root 2. So on the top, we're going to have root 2 cis of 3 pi on 4. Now we're still raising that bad boy to the power of 3. We draw a second diagram. 1 plus I is in the first quadrant. And again, this is very similar to that previous complex number above, except it's in the first quadrant. So here we've got theta, 1 and 1. So hopefully we should know by now tan inverse of theta is pi on 4, but since we're still in the first quadrant, the argument with the principal axis, or the principal argument, is going to be pi on 4. So this is root 2 cis of pi on 4. Now we still haven't applied de Moivre's theorem, that's our next step. So we're going to raise root 2 to the power of 3. Now root 2 times root 2 is 2, multiplied by 1 more root 2, we get 2 root 2. Cis of 9 pi on 4, 3 on 4 times 3 is 9 on 4, divided by 2, root 2 squared is 2, cis of 2 pi on 4, or pi on 2. Now we can apply our division law of complex numbers in modulus argument form. We're going to cancel those by dividing the moduli, and we get root 2 cis of 9 pi on 4 minus pi on 2, which is like 14 pi on 8 or something. 9 on 4 minus 1 on 2, yep, 7 pi on 4. Root 2 cis of 7 pi on 4. Now 7 pi on 4, the number 7 on 4 is less than 2. So that's within our within run revolution of 2 pi. So 7 pi on 4 is over here. So that's 7 on 4 there, 7 pi on 4. Now the reason I knew that 7 pi on 4 was in the fourth quadrant is because if we think of our angles, if you go straight up, that's pi on 2. If you go straight across, that's 1. Straight down, it's 3 pi on 2, and then all the way is 2 pi or 0. But if we forget about the pi and think about it just as decimals, going straight up is going up by 0.5. Going across is going across by 1. Going down is going down by 1.5. So 7 pi on 4, or 7 on 4, is 1.75, which is greater than 1.5 or 3 pi on 2. So it has to be in the fourth quadrant. It's not going to be back in the first quadrant again because it's less than 2 pi, or less than 2. Now, that acute angle there, sometimes we call it the related acute angle. This angle here is going to be pi on 4, because if you want to get to a full revolution, you only need one more pi on 4 to get to 8 pi on 4 or 2 pi. So we think about what's going to happen here. If we've got root 2 here, we've seen that so many times. If we have root 2 and then pi on 4, that's going to be 1 and this is going to be 1. So this is the complex number, 1 plus I. But again, I've purposely written it wrong because we haven't considered what quadrant it's in. So this is in the 4th quadrant. So we're going straight across to the right by 1, but down by 1. So it's 1 minus I. Again, I always like to confirm that I'm right on my calculator. It just gives you peace of mind during an exam. Yep, 1 minus I is the answer, so we're correct. Okay, this one's an example from the textbook. So we've got question 12 in the exercise. I believe it's exercise 1.3. We've got let z equal root 3 plus I, and w is the complex number z times by cos theta plus I sine theta. So part A says find the value of theta if w is purely imaginary. Well, let's think about for a second what purely imaginary means. All complex numbers, and all numbers in fact, have both a real and imaginary component. Now, most of the numbers that we've seen before we started extension 2 were real numbers. And we could say that these numbers were purely real numbers. That being that they only had a real component and not an imaginary component. Complex numbers are numbers that have both a real and imaginary component. So a number that's purely imaginary is a number that only has an imaginary component. In other words, in terms of our Argand diagram, all numbers that are purely imaginary will only exist along the imaginary axis or along the y-axis. So your purely imaginary numbers are only going to be up or straight down. Now we're told in the question that Im(w), or the imaginary component of w, is greater than 0, which means that your complex number w is simply a complex number going straight up. It's some complex number and it has to be only going straight up. We don't know where on the imaginary axis it is, but it is going straight up. So if w is z times by cos theta plus I sine theta, we're asking ourselves, what do I have to multiply the complex number z by to make it imaginary? So if we look at the complex number z, we've got root 3 plus I. Let's have a think about what that is. So z is root 3 plus I. If we draw a quick picture of that, it has a modulus of root 3 squared plus 1 squared, which is the square root of 4 or 2, ... This is root 3, and this is 1, and that is theta. So tan of theta is equal to 1 on root 3, and tan inverse of 1 on root 3, I'm pretty sure is pi on 6. Let me just double check. Yep, pi on 6. So theta is pi on 6. Now we're in the first quadrant, which means that that theta is in fact the argument with the principal axis, so we're all good. So z is the complex number 2 cos pi on 6 plus I sine of pi on 6. And w is the complex number 2 cos of pi on 6 plus I sine of pi on 6 multiplied by some complex number cos theta plus I sine theta. Now, using our multiplication rule of numbers in mod arg form, we can say that w is 2 times by the modulus of w, which we're not quite sure. This complex number here has a modulus of 1, so it's just 2 times by 1, because there's no number here. If there was, say, a 4 there, we would go 2 times 4, but there isn't 1 there. There's just a 1 there. So it's 2 multiplied by cos pi on 6 plus theta plus I sine pi on 6 plus theta. Now we're told that the complex number w is purely imaginary. Now if you're going straight up, that's because we're told in the question that it also is, the imaginary component of w is also greater than 0. So that's telling us we're going straight up. Now going straight up is an argument of pi on 2, or 90 degrees, and that's because the x and y axis, or the real and the imaginary axis, are at right angles to each other. So theta plus pi on 6 is equal to pi on 2. So that would make theta, if we subtract the pi on 2 over, to be pi on 3, I'm pretty sure. Yep. So we've just found the value of theta. So for part A, theta is pi on 3. Part B asks us to find the argument of z plus w. Now, if w is purely imaginary, we also are told that and we've also just found out that w has a modulus of 2, and it's also purely imaginary, so it's the complex number 2 cos pi on 2 plus I sine pi on 2. Now going straight up, for a number to be purely imaginary, it can only contain imaginary components. So cos of pi on 2 we know is 0, so that makes sense. Sine of pi on 2 is 1, so this is a complex number, 2i. So w is 2i. We also know that z, from the original question, is root 3 plus I. Now we're asked to find the argument of z plus w. So we're just going to add z and w together. It's as easy as that. Z plus w is equal to root 3 plus I plus 2i, which is, adding the real and imaginary components, root 3 plus 3i. So that is z plus w there. If we draw again a cute little diagram, that's going to be over there. The real component is root 3, and the imaginary component is 3. We put our theta here. So tan of theta is opposite over adjacent, 3 on root 3. Now 3 on root 3 is just root 3, so we rationalise the denominator there. And tan inverse of root 3, I'm pretty sure, is pi on 3. Right, so we've just found theta is pi on 3. Now we weren't asked to find the modulus, just the argument of z plus w. And since we're in the first quadrant, pi on 3, we're all sweet. So therefore the argument of z plus w is pi on 3. Alright, I hope that makes sense. That's de Moivre's theorem in a nutshell. Now, later on we're going to come back to de Moivre's theorem when we look at applications of de Moivre's theorem, and one of the best applications that the textbook and HSC exams like to do with de Moivre's theorem is finding formulas for exact values of more complex trig functions. Alright, hope that makes sense.